Type the word strawberry into the world's most advanced artificial intelligence, a system trained on the collective knowledge of human history, and ask it a simple question. How many RS are in this word? The machine, capable of writing complex software and passing the bar exam, will confidently look you in the eye and tell you there are only two. Ask it to reverse the word indivisible, and it will stumble, trip, and produce a jumbled mess of letters. This is not a glitch in its logic engine, nor is it a temporary bug that the next update will magically solve. It is a fundamental design compromise. The truth is, modern artificial intelligence does not read. It does not see letters, and it has no concept of spelling. Between the human prompt and the silicon brain lies a hidden, silent translator that slices our language into arbitrary mathematical shards. And right now, this translator is the greatest bottleneck in the history of computer science. To understand why the machine fails at basic spelling, we have to look through its eyes. When you type text into an LLM, the raw words do not reach the neural network. Instead, they are intercepted by an independent, pre-programmed algorithm called a tokenizer. This tokenizer is the AI's gatekeeper. It acts like a cookie cutter, chopping continuous human sentences into discrete fragments called tokens. A token can be a whole word, a syllable, or even a single punctuation mark. When the word strawberry enters the tokenizer, it is instantly split into two fragments, straw and berry. The model does not see STRAWBRRY. It only sees two distinct numerical addresses in its hard-coded dictionary. To the AI, the word strawberry is simply the sequence of those two numbers. When you ask how many RS are in the word, the model searches its memory for the attributes associated with those two numbers. But because it never saw the individual letters to begin with, it has to guess based on statistical probability. It is blind to the spelling because the tokenizer stripped the spelling away before the brain could even think. Most people assume that this tokenization process is a highly sophisticated, deep learning miracle of modern science. But it is actually a legacy hack. The dominant algorithm used by models today is called Byte-Pair Encoding, or BP. BP was not designed for artificial intelligence. It was invented in 1994 as a simple text compression algorithm, meant to shrink file sizes by replacing common pairs of characters with single bytes. Decades later, early natural language processing researchers ran into a massive wall. If you build an AI that treats every single word as its own unique unit, your dictionary becomes infinitely large. Slang, typos, and new technical terms will completely break the system because they are out of vocabulary. But if you process text letter by letter, the computational cost skyrockets, and the model struggles to see the big picture. In 2015, researchers realized they could repurpose the old 1990s compression hack. By using BP, they could dynamically break rare words down into small, common subword fragments. It solved the vocabulary problem, but it introduced a permanent structural blind spot that we are still paying for today. Imagine you are tasked with recreating a highly detailed oil painting, but you are not allowed to use a paintbrush. Instead, you are given a massive box containing exactly 100,000 pre-cut ceramic tiles. Some of these tiles contain whole objects, like a tree or a brick. Others contain generic patterns, like a blue sky or a blank white space. If you want to depict a forest, you can easily lay down a few tree tiles. But if you want to paint a highly specific, rare species of orchid that is not in your box, you are forced to combine random fragments of other tiles, perhaps cutting a pink flower tile in half and pairing it with a green leaf fragment. The final mosaic might look somewhat like the orchid from a distance, but the underlying structure is an awkward, fragile collage. This is exactly how a tokenizer works. The fixed box of tiles is the vocabulary size, usually ranging from 32,000 to over 200,000 tokens. If you use common words, the tokenizer lays down a single clean tile. But if you feed it something unusual, it must clumsily construct it from fragments. The AI is forever looking at a mosaic of tiles, trying to guess the smooth curves of the original brushstrokes. Because tokenizers are trained on raw internet data before the actual AI model is trained, they often contain hidden traps. This is the phenomenon of glitch tokens. During the pre-training of early models, the tokenizer crawled millions of pages of raw web text, finding frequently repeated strings and assigning them unique token numbers. One such string was SolidGoldMagikarp, the username of a prominent user on a Pokemon forum. Another was streamplot, a technical term from a Python graphics library. The tokenizer carved out dedicated, permanent slots in its dictionary for these specific terms. However, when the actual neural network was trained on clean, curated datasets, these bizarre usernames and code variables rarely, if ever, appeared. The result was a catastrophic disconnect. The tokenizer knew the word existed and had a number for it, but the AI's brain had absolutely no idea what that number meant. When users later typed SolidGoldMagikarp or streamplot into the commercial model, the neural network received a mathematical coordinate it had never learned to navigate. The model would instantly lose its mind, hallucinating bizarre insults, repeating lines of gibberish, or completely breaking down. A single, unoptimized entry in the hidden dictionary could completely bypass the safety guards of a billion-dollar system. This architectural compromise is not just a quirky technical limitation. It is a system of economic and cultural inequality. Because modern tokenizers are trained primarily on English-dominant datasets, their dictionary tiles are highly optimized for English words. A single English word almost always equals a single token. But when you write in languages with different scripts, like Japanese, Arabic, or Tamil, the tokenizer runs out of pre-made tiles. It has to fall back on basic, byte-level fragments to piece the words together. The exact same sentence that takes 4 tokens in English can easily take 30 or 40 tokens in Telugu or Korean. Because AI companies charge users by the token, and because model memory limits are defined by token count, non-English speakers pay a massive, silent tax. They pay up to 10 times more money to run the same prompt. Their systems experience significantly higher latency, and the model's context window fills up vastly faster. The tokenizer has inadvertently created a digital class system, where the efficiency of machine intelligence is directly tied to the language of its creators. Perhaps the most dangerous consequence of this translation layer is how it compromises safety. Security researchers have discovered that the tokenizer can be weaponized as an exploit engine. Because safety filters are often applied to the raw human text before tokenization or to the final token output, clever adversaries can insert invisible characters, zero-width spaces, or rare byte sequences into their prompts. To a human eye, or a simple keyword filter, the prompt looks entirely benign. But when the tokenizer processes these hidden characters, it groups them in highly specific ways that completely alter the mathematical coordinates sent to the neural network. By exploiting this blind spot, attackers can bypass safety guardrails, forcing models to generate malicious code, bypass copyright protections, or reveal sensitive training data. The safety teams are guarding the front gate of the fortress, completely unaware that the tokenizer is delivering Trojan horses directly into the throne room through a side door. If tokenization is so deeply flawed, why do we keep using it? The answer is pure computational survival. Right now, attempting to process raw bytes or individual characters directly inside a massive neural network is computationally brutal. It requires far more memory and processing power than our current hardware can handle. The tokenizer is a messy, compromised Band-Aid, but it is the Band-Aid that makes the current AI boom economically viable. However, the tide is beginning to turn. Researchers are actively developing token-free architectures models that can process raw characters and bytes directly without losing their conceptual grasp. Until these architectures mature, we must remember that the highly polished, seemingly human intelligence we interact with every day is still bound by a primitive 1990s compression tool. When you talk to an AI, you are not talking directly to a mind. You are talking to a prisoner looking through a keyhole, trying to reconstruct a world it can only see in broken, jagged tiles.